Hello and welcome back. In the last lectures, we have seen why to use FFT instead of DFT. We have seen the algorithm. Okay, but we are going to see how much the computational complexity is reduced in case of FFT. Okay, so first of all, we'll write the number of computations required for DFT. Okay, so I'll write only the complex computations, not the real. We have seen how much real computations are there referring the complex computations. Okay, so we'll not go into that detail here. Complex multiplications for DFT, that were n square, and complex additions for DFT were n into n minus 1. Okay, so now we'll see what are the computations required for this FFT. So we'll see complex multiplications and for FFT, complex additions for FFT. So here we'll see this is stage 1, stage 2, and this is stage 3. So in stage you can see each stage. This is the example for 8-point FFT. So for 8-point FFT we have 4 butterflies in each stage. There are 4 butterflies. So you can say that n by 2 number of butterflies are there. N by 2 butterflies for each stage. You can see here also 4 butterflies are there. Here also 4 butterflies are there. So for each butterfly we have a number, say W at 0 here, twiddle factor, multiplying this number. And here also for each butterfly we have this twiddle factor multiplication with this number, and the input we are multiplying with this number. Okay, and at this stage we are multiplying the twiddle factor with this number, this number, this number, and this number. So for each stage we have to perform complex multiplication, that is half number of times. So if n-point DFT want to calculate, then for this calculation you have to go for n by 2. For each butterfly one complex multiplication is there. Okay, and we have to multiply it to the number of stages, how many number of stages are used. Okay, so here for 8, 3 stages are required. Now how to calculate in general? Okay, so this FFT algorithm is always called as radix 2 FFT algorithm, because we are going to 2-point DFT calculation at the base. Okay, so for 8 you have to divide it first into 2 4-point DFTs, then into 2. For each 4-point DFT you have to go for 2 2-point DFTs. Okay, so likewise you have to go on dividing by 2, means you have to choose a number of points n, that is 2 raised to something. Okay, 2 raised to m. So here 2 raised to 3 is equal to 8. Suppose we want 16-point DFT, then we should use 4 stages, because 2 raised to 4 is equal to 16. So to calculate the number of stages, we must take log of n. Log of n to the base 2. So it is number of stages. Okay, so beauty of this FFT is we require to look at these numbers, go on calculating these points, then you don't require these points. From these points you can calculate this stage output, and from this you can calculate this. Okay, so we'll see now the number of computation. Number of complex multiplication for each stage are n by 2. Okay, n by 2 into the number of stages. So it will be n by 2 into log n to the base 2. Okay, and the number of complex addition. For each number we need one addition. Okay, number of butterflies into 2. Each butterfly we need 2 additions. Okay, so these are n additions for a single stage, and into the number of stages, that is equal to log n to the base 2. So you can see this number n square is reduced to this n by 2 log n. So because of this log introduced in this formula, the number of computations are reduced to so much less value. Okay, so we'll see some example. We'll take some numbers and compare the computational complexity. We'll see the speed improvement factor. Okay, so we will take n, the number of input points, and we just compare the complex multiplications. Okay, first we'll write for DFT and then for FFT. So DFT we need to calculate n square, and for FFT we need n by 2 log n to the base 2, and here we'll write speed improvement factor. So we'll take a ratio of these two. So first we'll assume the less number of points, that is equal to 4 points, that we can divide into two 2-point DFTs. So here 16 multiplications, complex multiplications will be required. So here n by 2 is 2 into log number of stages will be 2, so it will be 4, and the speed improvement factor for it will be 4. Okay, now we'll take 8, 64, and now we'll require n by 2, that is equal to 4, number of stages equal to 3, so it's 12, so we're near about 5. For 16 square is 256, 16 half 8 into number of stages 4, 32, so it is near about, no, it's 8. Now we'll go to large number of point calculation. So we've seen that this is 10 lakh plus, and we'll see 1024 half is 512 into number of stages 2 raised to 10, so it will be 10. So it is 5120. So it would take the ratio of 10 lakh to this 5000. So it is near about 204. So this is the thing. Speed is improved to a factor of 200 when we are going for this number of points, 1024 number of points. So this is great improvement. Okay. So this is the speed improvement factor. You can see as the n is going on increasing, the speed improvement factor is also increasing. So this is beneficial when you are using larger number of input points. So the computational complexity is reduced to a lot much larger factor. Okay. So this is the basic benefit, that is reduction in computational complexity of within DFT when you are using FFT algorithm. So that's why FFT algorithm is so famous and it is used very widely. In computers also you can find out the commands FFT. They are not calculating DFT. Okay, so FFT is used very widely. Okay, so now we'll see the other benefits You have seen the graph for the calculations. So when you are thinking of computing a DFT using matrix multiplications, you will be using n by n matrix. So n by n, so n square complex memory locations are required. Okay, complex means there will be requirement of two memory locations for saving real and imaginary number. Okay, so n square and this input n by 1, that also must be saved in some memory locations. Okay, so that much larger number of memory locations are required. But you can see stage wise computations. In the first stage, these two numbers are calculated from these two numbers. Okay. So you have to give one memory location to the Twiddle factor and these two memory location to the input. And once you calculate this, you don't need these numbers. So you'll save these numbers in the previous memory locations and the further Twiddle factor will be saved at this memory location. So memory locations are very less required in FFT. So if you are calculating n point FFT, then you require n complex number saving. Okay. So 2n real memory locations are required and n by 2 means n real memory locations required for saving this 4 Twiddle factors in case of 8-point DFT. Okay, so this is called as in place computation property of DFT. So in place computation, because of in place computation, you require a lot of less memory for the FFT. That is another benefit of using FFT. Okay, instead of using DFT. Now we'll see at the input you have seen the sequence was scrambled. Okay, so how to get that scrambled sequence? Okay, so index, we'll write index for x of 0 it was 0. Okay, x of 1 it is 1, so we'll write x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. Okay, so I'll tell you now how to calculate that, how to write that scrambled sequence, because if you use the sequence at the input of FFT as it is, then the output is going to be wrong. Okay, because that points are scrambled. When we do that division in even and odd sequences, this input is getting scrambled. Okay, so I'm writing these numbers, this 3, 4, 5, 6, 7. Okay, and in binary this number can be written as 0, 0, 0. All the numbers can be written in binary. So all these numbers are in binary, 0 to 7. Okay, you can see reverse order. So we are writing this way. Now we'll reverse this order: 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1. This is 0, 1, 1, 1, 1, 1. So your scrambled sequence x of n will be this in decimal. So this will be x of 0. So first point you must have observed that is x of 0, then x of 4, then x of 2, then x of 6, then x of 1, then x of, this is 5, x of 3 and x of 7. So this is scrambling of the sequence. This scrambled sequence you need to write at the input of FFT. No matter how many number of points you use. This is I'm showing for 8-point FFT. If 16-point FFT is there, You write the numbers in binary from 0 to 15, then reverse the order and get the scrambled sequence. So this is the bit reversal process required to write the scrambled sequence. Thank you.